second lecture in predicate logic and Venn diagrams. So last week we looked at doing Venn diagrams with two predicates, which means two circles. Today we're going to look at three predicates with three circles and then go through and do some examples. So while this may look a little bit more daunting, you're doing the exact same thing with just three circles instead of two. So instead of having four potential options, there are now going to be 8. So you have section A without B or C. Number 2 is A and B but not C. 3 is B and not A or C. 4 is A and C and not B. 5 is A, B, and C. 6 is B and C and not A. 7 is C and not A or B. And then 8 is not A, B, or C. So when we look at no A is B or every A is B, just like in last time how we do the shading, we would do the same thing here, but you'll notice that the shading will extend into the C circle. And the reason it extends into the C circle is because if I were to say no A is B, it doesn't matter if you have A, B, or C. It's saying that A and B can never be together. So where A and B are present, we have to cross that section out, even if C is also present. Same thing with every A is B. What we're saying is that if you find A in the world, you must also find B. So A and C does not include B, so it cannot exist. Now, when it comes to the particulars, using the word sum A is B, here we can't necessarily just put a question mark or a check mark in the middle section because there are two middle sections where A and B overlap. And so you'll have to put a question mark in each section because we don't know where this thing is. Or if I said sum A is not B, there are two sections of A with not B. So we need to put a question mark in both of those sections until we can narrow it down to get that check mark or the X mark. As with two circles, when we use lowercase letters, we're referring typically to an individual or something within the set of predicates that we're talking about particularly. And so here you will see it's the same as the last slide, only you are using a lowercase s in addition to the question marks to identify that there is an individual within those sets. You don't know where that individual lies. Now, when it comes to the validity of testing Venn diagrams, these Venn diagrams are helpful because they're actually going to show us whether the argument is valid. And so when we symbolize the argument and draw out the Venn diagram in circles, we want to represent the premises but not the conclusion. That means you fill in the Venn diagram for the premises but not the conclusion. You then look at the conclusion and then look at the Venn diagram and see if the conclusion is represented in the Venn diagram. If it is represented in the diagram, then I wouldn't have to draw anything else, right? The Venn diagram would depict what the concluding sentence is saying. This is a valid argument. If, however, I would look at the conclusion and feel as though I would have to still draw something in, that means that the argument is incomplete, it's invalid, there needs to be more to it. So fill in the premises and then ask yourself, does the conclusion represent what the picture looks like in the Venn diagram? So going through a couple examples, and please try and do these on your own. So stop the video here and work on all 5 steps of the Venn diagram, or 4 steps because I've given it to you already in standard form. So assign a letter to each predicate, rewrite the argument in standard form using those predicates, then symbolize the argument with a Venn diagram, and then lastly you're going to determine, is this a valid argument or an invalid argument. So here we have every lion is warm-blooded, no fish is warm-blooded, therefore no lion is a fish. Again, pause the video now and work through this on your own. So when we're breaking this down, we want to see that there are three predicates within this. There are lions, there are warm-blooded creatures, and there are fish. And so once we've assigned letters, we will rewrite the argument in standard form, and we get every A is B, no C is B, and then no A is C. After we have our argument in standard form, we will then fill in the premises only, remember, not the conclusion. Every A is B. If I said that every A is B, that means that there's no such thing as A that's not B, right? Because if I'm telling you that every A is B, A and B always have to appear together. And so I'm going to shade out any section of A that does not incorporate B. And that would be section 1 and section 4, if you remember the numbering. If not, it's okay. So now I know that that section doesn't exist. And my next premise, no C is B. So here, I cannot have a C and a B together. I'm saying that no C is B. There are no C and B together. So I'm going to cross out anywhere where C and B overlap. All right. So now I'm done drawing my Venn diagram. I want to look at my conclusion and ask myself, is that conclusion represented? And here the conclusion is no A is C, which means there's no such thing as an A and a C together. And it turns out that this is represented because anywhere where the A and C circle overlap is crossed out, which means nothing can exist there. So it is the case that there is no A is C, so I know that my argument here is valid. Again, think of drawing no A is C. If I were to draw no A is C using a red pen, I would cross out the A and the C overlap. But because it's already drawn for me, I know that my argument is represented and therefore it is valid, or my conclusion is represented, the argument is valid. If I would have had to draw stuff in, then my argument would be invalid. But here it is depicted, so we have a valid argument. All right, argument 2. Again, pause your video, try and work this one out. 4 steps, assign letters, rewrite the argument in standard form, draw the Venn diagram, determine whether or not the argument as a whole is valid. Pause the video now and please work it out for yourself. All right, so all Greeks are human, all humans are mortal, all Greeks are mortal. Again, we have 3 predicates, Greeks, humans, and mortals here. When we reassign the predicates, the letters, we will get in standard form an argument that looks like every A is a B, every B is a C, therefore every A is a C. And it might help if, when you're looking at these arguments, you're thinking to yourself, before even drawing the Venn diagram, whether or not the argument could be valid or not. Right? Here we actually have a valid argument. If every A is a B and every B is a C, then it should be the case that every A is also a C. And so our Venn diagram should turn out to be valid in this instance. So, just like last time, every A is a B. A and B have to be together, which means we will cross out anything that's not A and B. So we will cross out sections 1 and 4 again. Next, every B is a C. And so we're going to cross out everything where B and C do not overlap, because again, every B is a C, so B and C have to be together. And then lastly, we will see what our conclusion is going to be. Every A is a C. Is that represented? How would that look if we were to draw it? If I were to say that every A is a C, that means if you have A, you would also have to have C. And that is the case, because we already have that section of A not overlapping with C crossed out. So we know that this argument is in fact valid. If I would have had to shade more stuff, if I would have had to put in more question marks or anything like that, we would know it's invalid. But because it's already been shaded for us, it's a valid argument. Okay, so now we're getting into a little bit harder questions. We actually have to break down the argument now. So these are the 5 steps, and this is going to appear on the final exam. You will have to reconstruct the argument in standard form, assign letters to each predicate, then you will have to rewrite the argument using those letters, draw the Venn diagram, determine whether or not that Venn diagram is valid, whether or not the argument is valid. So when we look at this argument, that's not true. You admit that you have to be fit to be a rower, and some of the best rowers are philosophers. So you must admit that at least some philosophers are fit. So when we're reconstructing the argument, remember, it's always helpful to find the conclusion first and then determine from that what the premises that lead to that are. So here, the conclusion is some philosopher is fit. Now, it's interesting to note that when we say you admit that you have to be fit to be a rower, what that means is that every rower is fit, not every fit person is a rower, right? Because if you have to be fit to be a rower, right, that's the necessary condition. So every rower must be fit because fit is necessary. And then some of the best rowers are philosophers, so some rowers are philosophers, or some rower is a philosopher, right? We don't know if it's going to be one or many, so it doesn't really matter which verb tense you use there. After we determine the argument in standard form, remember we assign letters to each predicate. Here there are 3, rowers, fit people, and philosophers, and then we'll rewrite the argument in standard form. So here we have every A is B, some A is C, and some C is B. So from there, we can now turn that into a Venn diagram and see if the argument, or see if the conclusion is represented. So once again, every A is B. You'll notice that as you do this, there are not that many different ways to form these types of predicate propositions, right? There's only so many ways we can talk about sets when it refers to some and every. And so you'll notice that you're doing kind of the same thing over and over again. You're going to start to sense the patterns. You're going to start to see or become more familiar with how to fill out these diagrams. Every A is a B means that A and B have to be together, which means there's no such thing as A without B. So we will shade out anything where A does not overlap with B. Next, some A is C. So here we're saying that there's something in the world that exists that is both A and C. So we want to look, and if there's one section where we can put it in, we will put a check mark or an X. If there are multiple sections that we can put it, we will put the question mark because we'll need a little bit more information to narrow down where that thing is. So it turns out, however, that there is only one place where A and C overlap, and that's in quadrant 5, if you remember the numbers. And so that's the only place we know we get the check mark. We know that that has to be there. If, however, section 4, or quadrant 4, in the bottom part of where A and C overlap, if that were not shaded in, then we would have to put a question mark in quadrant 4 and 5. We wouldn't necessarily be sure. But because there's only one, we know that there's definitely something in that quadrant, and we can put a check mark. So then we ask ourselves, is the conclusion represented? Is it the case that there's something in the world that exists that is both in the C circle and in the B circle together? Yes, there is. This is another valid argument. Okay, moving right along. Argument 4. Again, pause the video. See if you can do this one on your own. 5 steps: reconstructing the argument, assign variables to each predicate, rewrite the argument using those variables in standard form, and then draw the Venn diagram, determine the validity. Okay, so all men are human and some humans are French, so some men have got to be French. Again, it helps to find the conclusion first. Some man is French is the conclusion. How do we know, or what information leads us there? Well, every man is human and some human is French, therefore it must be the case that some man is French. So once we have the argument in standard form, assign the variables, draw the Venn diagram. So again, 3 variables, man, human, French. Rewriting the argument in standard form, it looks like every A is B, some B is C, and some A is C. Again, same first proposition here. Every A is a B, shading out just like all the others. Next one, a little bit different. Some B is C. So there's something in the world that is both B and C together. Now we'll notice that there are 2 open sections where B and C overlap, quadrant 5 and quadrant 6. And so because there are 2, we don't know which one these some things are that we're talking about. And so we need to put a question mark in each of these 2 sections. Now, we need to ask ourselves, is the conclusion represented in the drawing? Some A is C. So there's something in the world that's in the A circle that's also in the C circle. Now, this argument is going to be invalid. This picture is not represented because we don't have a check mark in the A and C overlap. We don't know where this question mark falls. So if it were to fall in quadrant 5, then we would have a valid argument. But if it fell in quadrant 6, it would be an invalid argument. Also, because we don't know, it means we don't have enough information. We need a third premise to narrow down where this question mark actually is. And so our conclusion is not represented, and the argument is invalid. Okay, argument 5. Pause the video, try this one on your own. So here we have no logician is entirely sane. Morris is a logician, therefore Morris is not entirely sane. Again, pretty easy to pick out the conclusion here. Morris is not entirely sane. How do we know? Because no logician is entirely sane and Morris is a logician. So now when we assign predicates, remember that a name is not one of the predicates. That is going to be one of the lowercase letters that fall within the predicates, within the circles. And so here we only have a 2-circled Venn diagram. We have logicians and sane people, and then we have Morris lowercase m, where we're going to place inside or perhaps outside of these circles. Rewriting the argument in standard form, we see no A is B, M is A, M is not B. So with the 2-circled Venn diagram, no A is B, it means that you cannot have A and B together. That means we cross out the section of A and B that overlap. Now if we say M is A, there's only one open section of A, and so we are going to put our lowercase m in that section and ask ourselves, is the conclusion represented? Is it the case that M is not in the B circle? Yes. Yes, that is the case, and so we know that this argument is a valid argument. Okay, now this is another tough one. All physicists are scientists and only scientists are clever, so it follows that Max, a physicist, must be clever. Now, breaking this one down into standard form is a little bit difficult, and there is a trick to this one, and it's the trick is with the word only scientists. So when we use the word only in this instance, remember it will flip the conditions. It flips the necessary and sufficient conditions of only scientists are clever. So what we end up getting is something like all physicists are scientists, only scientists are clever, Max is a physicist, therefore Max is clever. But we can't keep only scientists are clever. We need to turn that into a universal claim or a particular claim using some. So it must be every scientist is clever or some scientists are clever. But remember, that word only will flip the conditions. So instead of it saying every scientist is clever, the word only will flip the condition and you will get every clever person is a scientist. Because if I were to tell you, right, only scientists are clever, in English what we are meaning is that every clever person is a scientist, not every scientist is clever. And so it's important to get that necessary and sufficient condition down to know that that word only will flip the conditions. So make sure you're aware of that and determining what is necessary, what is sufficient when we're reconstructing these arguments and reforming these propositions using universal claims or using particular claims. So the correct breakdown is the one on the bottom. Every physicist is a scientist. Every clever person is a scientist. Max is a physicist. Therefore, Max is clever. Here again, going back to the three-circled Venn diagram, there are three predicates and a person's name. So we're going to get three circles, and then we're going to have a lowercase letter that we will be placing within those circles. Every A is B. Every C is B. M is A, therefore M is C. So again, every A is B, crossing out the A section where the B does not overlap, A and B does not overlap. Every C is B, which means you cannot have C without B, so you're going to cross off everywhere where C does not overlap with B. One of those sections already crossed off. We can do it again, doesn't matter. Now we want to know M is in the A circle. So you will notice that there are two open sections or two open quadrants in the A circle, quadrant 2 and quadrant 5. So we must put an M in both of those sections. Now we can ask ourselves, is M in the C circle? Not necessarily, right? We don't know where it is. We need more information. If it turns out that it's in quadrant 2, then this is invalid. If it were in quadrant 5, it would be valid, but we don't know. And so we need more information. Our Venn diagram is not complete. This argument is invalid. Now, going over this, I just want to mention a little caveat that comes into using Venn diagrams with predicate logic. Just so you don't think that this is going to answer all of your questions to determining good from bad arguments, there are some small little exceptions that go into predicate logic and Venn diagrams. And so looking back at the square of opposition, we can see that the particular claims will contradict the universal claims on the opposing side. So the contradicting statement of every cat is tame is some cat is not tame. And then the contradicting statement to no cat is tame is some cat is tame, and vice versa. Now, it's the case that there are these references of subalterns or anything from the universal can be deduced to the particular. For instance, every cat is tame. From that, I can take that there is some cat in the world that's tame, right? So if I'm looking out at a field of cats, right? That would look incredibly weird, but let's go with it. It would be fun, right? A field of cats. If I were to take one of those cats, I would know that some cat is tame, because if every cat was tame, then some cat must also be tame. Similarly, if no cat is tame, then I could take one of those cats and I would know that this some cat is not tame. So the particular comes from the universal in this instance. The problem with this is that it's not always the case that that happens. If I were to change cats to something like the zombies and say every zombie is dead, right? It necessarily wouldn't lead me to believe that some zombie is dead, because zombies are not real. And so while I can imagine that every zombie is dead, there is no such thing as some zombie. So when we think back to a Venn diagram, we can see crossing out a section makes sense. But just because we cross out a section, it doesn't mean there's something left in the open section. And it's these two, right, the founders, fathers of predicate logic, that really give us a way to sort through this dilemma. And it's by introducing a different type of language, really, to predicate logic. Don't worry, you will not have to know this. It's just there as kind of a reference to show you that there's a way around these exceptions. But for Venn diagrams, for the purpose of Venn diagrams, we're not going to be talking about this at all. This is the next step up if you want to take symbolic logic or a more advanced logic course. And so we can see the problem with the argument that every cat is a mammal, every cat is furry, and some mammal is furry. So here we have three predicates, and then when we look at this argument, every A is B, and every A is C, we see that there's that open section in quadrant 5. The problem here is that some B is C. This conclusion is not represented because in order for the sum B is C to exist, you would need that check mark in a B and C overlap, but you do not get it. Because we have not affirmed in this instance that cats exist. We're just saying that if it's a cat, it's a mammal. And if it's a mammal, it must be tame. But we're not necessarily saying that there definitively are cats. So one of the problems, or the main problem with predicate logic with these Venn diagrams is this kind of deeper philosophical metaphysical question of does the shading really lead to the existence of something? And no, it's not the case that is. However, this isn't necessarily anything you need to concern yourself with at this point. This is basically just kind of telling you about the exception. None of the arguments that we're going to look at in this class are going to pertain to this exception, but it's just helpful to know so that you're not going off on the street pretending you know everything because you can draw Venn diagrams as if anyone would